We come to now the discussion of forces that are acting on the control volume. We started with Newton's laws of motion. Then we came to in a fluid flow the choice of a control volume, and now we see what forces are there that act on a certain control volume, and we have to keep them in mind, take them into account when doing our mathematics or calculations. The forces acting on control volume consist of body forces that act throughout the body of the whole control volume that is under consideration. And such forces are gravitational forces, electric forces, magnetic forces, and indeed, most importantly, well, not most, all of them are important, and surface forces. Now, many of the forces we don't see normally, and we don't even consider them in a fluid flow motion that we come across in our daily life, such as electric forces or magnetic forces. But there are cases in which these forces become important and we cannot ignore them. But otherwise, mostly gravitational forces or surface forces are more frequently found. And pressure and viscous forces are, of course, are there, and so are reaction forces at points of contact. Only external forces are considered in the analysis. The total force acting on a control volume, when we choose a control volume, we try to see that how do we compute them, how do we calculate them and take care of count of the external forces that are occurring. And we write the equation as summation of S, the total external forces composed of the total body forces, all body forces that I mentioned in the previous slide, plus the surface forces. And of course, all of them have different impacts, different effects, and therefore even different terms in the equations of motion that we develop. The total force acting on a control volume is composed of body forces, as we mentioned, and surface forces. Body force is shown on differential volume element, and the surface force is shown on a differential surface element. That is, in the given picture that you are seeing, a control volume is of course arbitrarily chosen and is reflected in a dotted red line. So this is arbitrary choice. We can increase it, we can decrease it, but so it is. And just to represent within it, we take a small differential volume element, a small volume having dimensions dx, dy, and dz, for example. So if this we take as origin, and then this is dx, this part dy, and this part as, let's say, dz. So the product of them, dx, dy, dz, is a volume, is represented here as d of v, where this v is not velocity, it represents volume. And the body force, mainly that is gravitational force, and gravitational force act in the downward direction, and therefore you can see that its direction is shown as acting downwards. So that is the body force, and these are the forcing, and so you can consider them and see in which direction and how they are acting on a small volume, differential volume within the control volume that is under consideration. And on the surface, at this diagram, a small surface element is picked up. This is right on surface of this, and that is why you can see that it has a curved nature. It's not in a straight line, it's not linear. It has a curve in all directions. And the force, since the force also has a direction, and it always acts in a direction that is perpendicular to the surface. Or if it is a curve, if the nature is of a curve, we call that perpendicular as normal to the surface. So therefore, we have shown the unit vector n showing the direction of the force acting on the surface. And DFF force you can see being shown here. The most common body force is that of gravity. We have mentioned that, which exerts a downward force on every differential volume of the control volume. So control volume is a bigger element of the fluid flow, and within that, of course, the differential volume is a smaller component that are all arbitrarily chosen. So the gravitational force is represented by dF as gravity, and this is gravity is G. So rho into G into D volume V acting over the volume. So that will be the total force that is acting on a differential volume. Gravitational vector in Cartesian coordinates. So normally, since G acts only in downward direction, therefore its x component, if I may write it as Gx, is 0. Its y component is also 0, and therefore its only non-zero component that acts is in the vertical direction. And if that is normally taken as z in our rectangular coordinates that are mutually perpendicular, and we write G as minus G times the unit vector k in the vertical direction. And since the gravity is acting in the downward direction, the positive direction is considered to be in the upward direction. Therefore, you see a minus sign appearing. So when writing mathematical equations to develop the equations and also to understand and analyze the forces that are acting, remember taking note of the sign of the force, the direction of the force is as much important as the force itself. The total body force acting on the control volume is the total body over rho g dV, and we integrate it over the total control volume. So if we integrate it, we get, since G has a constant value, of course it has a direction, but in terms of numbers, so therefore when we integrate it, we may get mCV, that is mass, total mass of the control volume times G. And the total force is therefore look like as summation of all external forces equals sum of summation of all body forces plus the pressure that is there, the viscous forces, and any other force that may be present, and all of them are clubbed as surface forces, while the gravitational force is taken as separately. And here, as is obvious, the body forces also include magnetic or electric forces, and we are assuming that they are not acting here, they are 0. So that is why they do not appear, and only the gravitational force is shown. So that is how the total force is acting on the control volume that we are considering.